So now we'll be looking at the square root x or square root functions. So these are also quite the general shape of square root functions is the half of a sideways parabola. So that sounds a bit that sounds weird, but a sideways parabola is something like this or this, and then if you take the half, well, that or that or that or that. It's not really an exponential function, but something, it kind of resembles it. So how do we do this? So basically, if e is greater than 0, the shape of the function is something like that, and if a is less than 0, well, the shape of the function is something like that. So if you guys know the implied domain for a square root function, well, x cannot be negative. If x is negative, it will not be a real number anymore. The function will have imaginary values, which we do not consider, and therefore which imaginary values which we can't really graph. So if you notice any square root function at x is equal to 0, the function will just stop. That is the this can be from here or here, but it cannot cross the y-axis and move on to negative x terms, because that would be that's not possible within the domain of real numbers. Just remember that the y-axis is not a vertical asymptote, as a function actually comes in contact with the y-axis, because root of 0 is still possible, but it cannot cross the y-axis and move on to negative x terms, because the root of negative x terms is imaginary. Square root functions work if you get plus c or plus any constant or divided by 2. Some changes to this will again be covered in the transformation video, but this is the basic shape. So this is the basic shape. If a is greater than 0, it slopes upwards, and if a is less than 0, it slopes downwards. So you have to find the y and the x-intercept. So you have to find the x-intercept is always 0, but you have to find the y-intercept. And so to be noted, there is no horizontal asymptote at this point. It just keeps decreasing beyond a point, but there is no horizontal asymptote. This is because the square root function can be thought of as the inverse of a quadratic function, and quadratic functions have no asymptotes. Likewise, square root functions also have no asymptotes. So do not confuse yourself. This is just the shape of the function, and why the shape exists, and to figure out why the shape exists, well, you can substitute values into the function yourself and see that square root functions follow this specific shape. So now we're covering the modulus of a function. This can be any function, and there are two types of modulus functions that you should be knowing. One is the modulus of the whole function, and another is the modulus of just the x terms. So basically no negative x terms. So how do you go about doing this? So in the first case, how do you sketch a function? So basically you sketch f of x, and then you reflect everything, and then you reflect everything below the x-axis to above the x-axis, and then you keep the other parts as well. So why do you do this step? So basically, if you have a function, something like maybe a parabola, well, the modulus function, the corresponding modulus function will look something like that. So basically, all this part has been reflected upward. This is because, well, you cannot have any negative y terms, because you're doing the modulus of all the f of x values. So since y is equal to f of x, you cannot cross the x-axis, and therefore all the values which cross will be converted into positive values. That's why you have to reflect about the x-axis at that specific region only. So I think this is quite self-explanatory, and if you guys understand how modulus functions basically work, which they basically take the absolute value of any term, which means they remove the negative sign in front and only take the positive aspect of it. So that's why we have to reflect over the x-axis. The second thing you have to learn about modulus functions is f modulus of x. So over here, the modulus is not being applied to the entire function, which means negative y values can exist, but there are no negative x values. So if positive x values produce negative y values, those are still allowed. But if there are any y values which correspond to positive x values, those cannot be allowed. So that might sound a bit confusing, but let's look at how we actually sketch the graph. You'll get a better understanding. So basically, you sketch the graph for all values of x greater than or equal to 0. So make sure you sketch all the values for x greater than or equal to 0, because less than 0 is not allowed according to modulus functions. So after you do that, you just reflect whatever you drew over the y-axis and keep the positive part which you drew over here as well. So okay, so as you can see, let me give you an example. Y is equal to sine x. Let me just extend that graph. Now we're going to sketch y is equal to sine modulus of x. Well, that would be, so first we sketch all the values for x greater than 0. So that would be something like that. And then we take this part and reflect it over the y-axis. So it will be something like this. So as you can see, it's different from y is equal to sine x. Why do we do this? Why do we do this? It's not that negative x terms don't exist, but because in a modulus function, f of x should be equal to f of mod negative x, because the negative sign is negated, and therefore, well, the negative sign shouldn't matter, so it should be equal to the exact same value of, as f of x. So that's why if you take this point as 1 and this point as -1, the f of x value should be exactly the same, and that's why we reflect the drawn part over the y-axis. I hope that keeps things clear. And again, for transformations like adding a constant or dividing the whole thing by 2, stuff like this will be covered in the transformations video. Talked about this. So I briefly already talked about this while discussing logarithmic functions, but this is quite simple. So any graph you take, if you want to find the inverse of that graph, well, you just draw y is equal to x and then reflect it over that line. So this would be the line of symmetry. So I think that's pretty self-explanatory, and yeah, it's quite basic. So let's look at the following hybrid function. So if you look at, so hybrid functions sound way more complicated than they actually are. They're actually super simple. So basically, hybrid functions are, you just, to sketch hybrid functions, you just look at the 3 domains given. There's the first, there's the second, and this is the third domain given. So for the, you basically look at them as individual graphs, and then you just join them together. So if I take this graph, well, for x is less than or equal to -1, well, let me just mark -1, we're sketching negative x. So the graph will look something like this. This is basically a linear function, and it's super simple to sketch. And between -1 and +1, we're sketching the graph y is equal to 1. So y is equal to 1 would be something like this. So this y-intercept would be 1. And then from x is greater than or equal to 1, we have to sketch the graph y is equal to x, and that is pretty simple again. So this is basically the graph. There are 3 points, and yeah, so it's quite simple. But the idea of continuity comes in here. Continuity. So basically, there are 3 types of continuity. So it goes continuity. So the idea of continuity comes in here. So there are basically 3 types. So the first one is jump. The second one is asymptomatic. And the third one is missing point. So how that works is, in the case of jump, the 2 graphs basically, like in this case, it's a regular type of continuity, and let's look at an example. For example, so the graph would look something like, well, for until 0, it would look something like this, and then from 0 it will go something like this. To be noted is that this point is not included. It's basically like less than 0, so it's not less than or equal to. But as you can see, this is called jump continuity. So basically from this point, it jumps down here and then continues the graph. So that's the first type. And then, well, if a function is suppose like this, if there's a function which has a graph something like that, and then the function continues this way where it cannot touch this, where x is equal to 0 is an asymptote. Well, that's an asymptotic, that's called asymptotic continuity, so that's quite simple. And then the last is missing point. Sometimes, and this is quite rare, but just something you can take note of. It's not very important either, so it's just, well, sometimes a graph could be going like this, stop at this point, and then the next function may be starting from here. Basically, this domain is not defined, and this is called a missing point continuity. So yeah, that's just things to keep note of. They're not very important to name, but yeah, continuity often appears in these forms, and it's quite simple, and I think you guys should know it. And lastly, we have rational functions, and these also include reciprocal functions like 1 by x and stuff. So this is actually quite complicated, and I think it deserves its own video. So okay, I've made another video just specifically for rational functions, and that will appear in the cards right now. And yeah, I'll make another video for transformations because the graphs I've covered here are just the basic forms of these functions, and these can be modified by adding a constant or dividing by a constant, multiplying by a constant. There's a lot of ways you can modify it, and so go check that out as well. All the links will be in the description, and I would make a video covering examples of how to sketch this graph if you guys leave a comment below. And if I've made that video, it'll be in the cards or it'll be in the description as well. So thanks for watching, and hope this video helps you guys.